Yeah, the big takeaway or the big picture stuff is trying to separate the Cascadia subduction zone earthquake hazard, which is capable of producing a magnitude 9, which could really be devastating to the Pacific Northwest, from the San Andreas related deformation, so the stuff that's happening in central and southern California, where we consistently see magnitude 7s. And so we're putting this seismic array out in a location that is right at the, the nexus of where those two systems meet, and trying to disentangle contributions from subduction versus San Andreas. So the array that we put out is called SCENTAR, the Southern Cascadia Earthquake and Tectonics Array. So this is an NSF funded project that is really aiming to understand how we have built such large mountains in the northernmost California area. They're much larger than what we see as you go up into Oregon and Washington, still along the Cascadia subduction zone, and also larger than what you see further to the south in California. So we want to understand what's controlling that mountain building process. Mountain building processes are commonly linked to high amounts of earthquakes, because in order to build mountains, you have to break the earth.
Well, Northern California is like on the Cascadia subduction zone margin. So that's where like basically two plates are like, colliding. One is subducting beneath another. And what is really happening is that the Cascadia subduction zone hasn't produced a very like big earthquake in the last 300 or years. It is currently accumulating strain, and so there's like this probability, or there's this chance that scientists have been they've been anticipating for like a big earthquake.
There's two hazards here. I mean, we have this 9.0 earthquake that's going to happen, right? That's going to cause a lot of damage. And understanding Cascadia better helps us understand the threat and the chance that Cascadia will eventually let go and rupture.
So when all is said and done, I think what we'd really like to have in this area, or what we'd really like to have from this project, is a better understanding of this portion of the western United States that's actually relatively understudied. There's a lot of focus on the San Andreas Fault in California, and there's a lot of focus on the Cascadia subduction zone up in the areas of Seattle and Olympia. But one area, largely because it's relatively underpopulated, compared to much of the West Coast, that there hasn't been a ton of work done, is this region between about Redding, California, and Eugene, Oregon. We have this large mountain building, we have these large mountains that have been built that kind of separate it, make a really dramatic features in the topography. But due to its ruggedness and kind of remoteness, not that many people have dug in and with modern techniques to understand that area better. I would call myself a tectonicist, but most of the tools I use are seismic imaging tools. So that would be the equivalent of a CAT scan or an X-ray that we do in the human body, but we're aiming into the earth, and we're looking at about the upper 70 miles of the earth in this case, to understand areas that might have potential for earthquakes, or what processes are leading to mountain building in this portion specifically of the Cascadia. So we put out 60 what we call nodal seismometers. They're relatively small instruments that record all three components of ground motion, so we can fully characterize how the earth is shaking.
I didn't think there was any earthquakes happening over there, because there's just nothing that's being detected. The sensors went in, and all of a sudden it's like, wow, they're everywhere. They're small, they're not strong, people aren't feeling them, but it tells me that that area is indeed moving, and it does have an earthquake threat that we can't be ignoring.
Previously in the past, people have been using kind of like borehole drilling and seismic reflection studies, which is actually like they use like big instruments, and it's very like extensive and manually intensive. And so what we're trying to do is like we're trying to use a method that actually just uses earthquake data. So it's easier and it's like cheaper. We look at like the Earth's structure, and then depending on like the structure, we can assess like how much of ground shaking is it gonna experience if there was an earthquake.
But there's been a lot of new methodologies developed within about the last 10, 20 years that allow us to use pretty short deployment durations and still get seismic properties, seismic images that are comparable to what we used to need a couple years of a seismic deployment for. We're only sampling pretty small time period on geologic scales, but it'd be equivalent to, let's say, taking an x-ray of your arm and then using that in a couple years. You know, your arm, assuming nothing happened to it, hasn't changed its structure all that much if you're not growing anymore. The Earth's always moving, but the changes in the Earth take, you know, generally millions of years to actually be expressed clearly, right? So it's the cumulative earthquake deformation that leads to the building of a mountain over millions of years, whereas one individual earthquake, they usually don't lead to that much topographic building. Preliminary analysis of our data set has seen that even in that 38 days, we recorded about 2,000 earthquakes in the area. Now, most of them are far too small to be felt. We're dealing with magnitude 1s and less. You know, we do have some magnitude 3s that occurred, which some people may have felt in the region, but the vast majority of these are very small seismic events that are just occurring very regularly in this area because of the interactions of these 3 different plates basically running into each other at this single spot.
Tsunamis can impact anywhere on the the coastline, but the Pacific coast is obviously the most impacted area because we have the most earthquakes out here. The vast majority of tsunamis are generated by earthquakes, volcanic explosions like we had several years ago. So that's the sort of thing that can cause a tsunami, and those are all mostly Pacific. So for us, it's the biggest threat here on the West Coast. And for Northwest California, we have Crescent City. There's just something about the terrain. There's a ridge line that goes out into the Pacific that directs tsunami waves this direction. So Crescent City often is hit by any tsunami wave that's generated in the Pacific. It's like a tsunami magnet. And unfortunately, that's a big problem for us because even distant source tsunamis can be a huge impact here and can destroy that harbor up there. Back in 1964, it actually inundated the land and killed multiple people in the town. So it's a huge threat even from far away, but also we have Cascadia right here. It starts in our region and goes all the way up to Canada. Someday is going to create that big earthquake that's going to impact the region. So NOAA has a couple of roles. The main thing for us here in Northwest California would be for the Weather Service is to warn people about the hazard. So when a tsunami is generated, someday it will, it's going to come across the ocean or it can be really close. We have to issue the emergency alert system message to let people know that the tsunami is on its way. That is, the sound that comes across with a tornado warning, same sort of thing. Only it would be tsunami warning, get out of the tsunami zone and evacuate to high ground.
I'm also part of another project called Crescent, the Cascadia Region Earthquake Science Center. And that's a collaboration between people that use satellite imagery to understand surface deformation or really high resolution GPS that can get at the millimeter scale displacements over year time scales, to people studying tsunami deposits from large run-up of ocean waves, and they can date those and look at get a sense of earthquake recurrence cycles and size, and then multiple types of seismologists. So you can have people that, like me, that are doing basically the equivalent of x-rays or CAT scans of the interior of the Earth. But we also have another community that studies the actual earthquake physics. So what causes an earthquake to happen, where.
I feel like it's not only important to me, I feel like it's important to like the whole society, because like we've seen like the devastation that like subduction zone earthquakes have produced, and subduction zones have produced the most powerful earthquakes. For example, the Tohoku earthquake, right, in Japan, that caused a tsunami as well. And so if we're able to like just kind of like help assess and like help people prepare for it, I think that would be like really like amazing.